reciprocal of a linear function. So if we reflect back on grade 9, grade 10, grade 8, a linear function is any function that results in a line being drawn. So forms of that were y equals mx plus b. Standard form was ax plus by plus c equals 0. Basically anything where the x and y are only raised to the first degree. Okay? Now, we also know things about polynomials. If you take some polynomial, let's say f of x, and you multiply it by another polynomial, let's say p of x, the result is going to be another polynomial function, okay? It's just going to be these two polynomial functions with even greater powers of x, and the terms are going to be lined up, connected by addition and subtraction. It's just going to be another polynomial function. But if you divide polynomial functions, if you wrote f of x divided by p of x, you end up with what is called a rational function. I'm going to take better notes on this in a second for you. This is just giving us some intro. A rational function. Well, let's think of any number, really. Any number can be written as a fraction. So let's say I took the number 7. I could write it as a fraction, okay? It's a rational number. Or the number 3 over 4. It's a rational number because it can be expressed as a fraction. Well, the functions that we're working with now can be expressed as fractions. Polynomial fractions. A polynomial over another polynomial. The easiest or simplest rational function is the reciprocal of a linear function. So basically, if you were to take, let's say f of x equals 2x plus 7, we were going to take the reciprocal of that. Well, what is this? It's really 2x plus 7 over 1, or 2x over 1 plus 7 over 1, right? Same value. If we take the reciprocal of that, we're really just flipping it over. So the reciprocal of that would be 1 over 2x plus 7, in which case you would have the polynomial in the basement, in the denominator. This is what makes it a rational function, as soon as you have a variable in the denominator. Okay, good. Let's take some notes on that in that top little space that you have. When you add, subtract, or multiply, two polynomial functions, the result is another polynomial function. That part's pretty straightforward. When you multiply whole numbers, you get another whole number. When you multiply polynomials, you get another polynomial. The result is another polynomial function. But when you divide polynomial functions, comma, you get a rational function, a function that needs a fraction to be expressed. So, when we get into this, quite often when we factor a polynomial, the goal, so let's say we have ax plus bx plus c in the denominator here, and we want to split it into its fractions, x minus r, x minus s. Well, one of the properties of numbers is that you can't have anything over 0. So when we're dealing with rational functions, and we are able to factor it, and let's say we said, okay, well now x equals r, well actually x can't equal r, because if it did, the denominator would be 0. Denominators are never allowed to be 0. It's an undefined number. So then there are restrictions on rational functions. In this case, x can't equal r and x can't equal s. Okay? Today we're working with linear functions, so it's a little bit easier to work with, but we get into all of that. Okay? So the bottom half of page 5 there, we have a few more notes. It says the most basic linear function is y equals x. Y equals x. We even know what it looks like, right? It's a diagonal line, goes through the origin. Y equals x, okay? A rational function is a function that has the variable in the denominator. The most basic rational function is y over x. It's a rational function because the variable is in the denominator. So the graph of y over x looks like this. Y equals 1 over x, I should be saying. Notice the graph comes close to the y-axis, but never touches it. That's in your notes there. The graph comes close to the y-axis, y, but never touches it. Okay? It also comes close to the x-axis and never touches it. But generally speaking, we'll talk about vertical asymptotes at this point in time. We'll also talk about horizontal asymptotes. But for the sake of our definition, as you're traveling along, because x is the input, right? So you're putting in, let's say, you know, negative 100, and then you put in negative 50, and you put in negative 25, and then you start getting closer like 10, 5, negative 1. And then when you get to when you put in 0 for x, what happens? The denominator is 0, so it's undefined, okay? But as you get closer and closer and closer to putting in, well, cut that part out, but the graph comes close to the y-axis but never touches it. So then we need a definition for our asymptote. An asymptote is a line that the function approaches but never touches. An asymptote is a line that the function approaches but never touches. So in this example, our asymptote, our vertical asymptote, is the y-axis. Okay? As our curve comes up from the right, it gets closer and closer and closer to 0, but it never touches 0 on the x. It never touches x equals 0. It goes way up to positive infinity. And you can think about that by knowing that this x is in the denominator. So as x gets bigger and bigger and bigger and bigger, so you have 1 over 10 and then 1 over 100 and then 1 over 1,000 and 1 over 1,000,000 and 1 over 900 million, then the value of the function is actually still going down, getting closer and closer and closer and closer to 0, but it never actually touches 0 because it's always one part out of all of those, okay? Then if you look at it from right to left, as x gets closer and closer and closer to 0, well, this number gets 1 over 1, which is 1, which would be right there. And then what happens? Well, it goes 1 over 0.5, which is 2. And then 1 over 0.1, which is 10. And then 1 over 0.01, which is 100. And then 1 over 0.001. And as you get closer and closer and closer along the x to 0, what actually happens to the whole function is it goes bigger and bigger and bigger. Okay? Same thing happens in negative land over here in quadrant 3, but we'll get into that in more detail as we move along. All right, in example 1, we have f of x equals 1 over 2x minus 1. We want to state the domain, which means we want to find any restrictions. Then we're going to describe end behavior. We're also going to describe the behavior near the vertical asymptote. So you're going to learn some new language. As x does this, y does that, etc., things like that. And then we're going to sketch a graph and state its range after we've sketched it. So we have f of x equals 1 over 2x minus 1. Now this is the reciprocal of a linear function. This is the easiest form of rational function. It just has a 1 in the numerator. It gets more complicated when we have another function involving x in the numerator. Then it gets a bit more complicated. Okay? First things first, state the domain. Well, what has to be true about x? Any restrictions on x? Anything x can't be?
Can't be 0.5.
Okay, good. So we know that 2x minus 1 can't be 0, because that would make this whole function undefined if the denominator were 0. So, simple algebra, we're going to add 1 to both sides and divide by 2. X cannot equal 1/2. So then our domain is x belongs to the set of real numbers, but x cannot be 1/2. Okay? Now if we know that x can't be 1/2, and actually we can do a little work on our graph as we go along. So you can find where x is 1/2 and put a little dotted line there all the way down at x equals 1/2. That is the equation of our asymptote, okay? If x equals 1/2 is a restriction, then it's also the equation of the asymptote. The equation of this line is x equals 1/2. And we've put it on our graph to indicate that the graph will never touch that line. It will approach it, but it will never ever touch it, okay? Let's look at B, the behavior of the function near the vertical asymptote. So now this one, we need to look at what is happening as this function approaches from the left. And then we want to look at what's happening as it approaches from the right, because we know that this graph is going to get split up into two legs. It's either going to look like this, okay, or it's going to look like this along the axes. If you can see that, okay. It is going to look more like the second one in this case, yeah. Okay, so let's figure it out. In order to do that, we need this language. We need to look at as x approaches 1/2 from the left. That's done with indicated by a little negative sign. And we're also going to look at as x approaches 1/2 from the right. And that's done by a little positive sign. I'm going to write that as x approaches 1/2 from the left, and this is as x approaches 1/2 from the right. Okay, we're going to lay this out in a chart. So we're going to put our x values on one side and see what's happening to the function. And we want values that are heading toward x equals 1/2 from the left. So we'll start with 0, we'll jump up to 0.4, and jump up to 0.45, 0.49. And all we have to do is plug them into our function and see what we get. So if we plug in 0 for x, we get 1 over 0 minus 1. That's 1 over -1. That's -1. Okay, if we plug in 0.4, you get 2 times 0.4, which is 0.8. You subtract 1 from that, you get -0.2. 1 over 0.2 is 5. And one of the factors is negative, so we're looking at -5. Plug in 0.45 for x, you get 0.9 minus 1, which gives you -0.1 in the denominator. 1 over 0.1 is 10, and we have a negative factor, so it's -10. And same principle applies. You put 0.49 in there, you end up with -50. So now we can see what is happening as we approach our asymptote from the left, reading left to right, kind of like this. Okay, this is going down, 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 way into negative land. Okay?
Would we write y approaches negative infinity?
Right, so you could say as x approaches 1/2 from the left, comma, y approaches negative infinity. In this case, it's not called y, our function is f of x, but then we could say f of x approaches negative infinity. All right, so if we add that to our graph, what does that tell us? And by the way, what do you notice about all of these values? The value of the function? They're all negative. Okay, so this thing is starting below 0. It's really, I'm drawing, this gap is, it should be infinitely small, really. I'm just drawing it this way to distinguish. I can put it a little closer. Okay, and as you get closer to your asymptote, you start to curl down. And quite often I'll just do my 2 straight lines like that, and then I'll come in here and finish the curve. So that it looks clean and crisp. Okay, that's one leg. It's approaching positive 1/2 along the x-axis, and as it's doing that, it's going down, 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 down. It will never touch this asymptote. It will get closer and closer and closer and closer infinitely. Okay? Same thing as x approaches from the right. This time we're looking at a chart where our x values are going to be coming down from 1, 0.6, 0.55, 0.51. That's enough test values. And again, we plug this all in. When we put 1 in here, we get 1/1, which is positive 1. When we put 0.6 in here, we get 1.2 minus 1, which is 0.2. 1/0.2 is 5. It's positive. When I put 0.55 in there, we get 1.1 minus 1, which is 0.1. 1/0.1 is 10. It's positive. And you guessed it, the next one is positive 50. Notice how the same numbers apply if you go the same distance away from the asymptote on your x values. At any rate, what's happening here? F of x is approaching positive infinity. So now this is the kind of the one time when we read graphs backwards, because we are approaching from the right. So we're looking at this thing from the right, coming toward the asymptote, and as we do that, it's going to curl up to positive infinity. And so we've been able to draw it. And really, I cheated a little bit, actually. I jumped ahead. Really, all we found out was, if I erase the part of the graph that we never actually found out yet, we didn't find out anything about end behavior yet. We only found out what's happening as x approaches the asymptote, okay? So we really only have the part that goes down to negative infinity and up to positive infinity, but we don't have end behavior yet. That's step C. And in step C, we're going to follow essentially the same procedure. So I'm just going to erase that part. In C, we're looking at end behavior. So end behavior is as x approaches negative infinity. That's what's going on over here to the left. And as x approaches positive infinity, that's what's going on as x gets bigger and bigger and bigger. So again, we can make a little chart. X values, value of the function. Let's go with -10, -100, -1000, -10,000. And then over here, as x approaches infinity, we'll use the values 10, 100, 1000, 10,000. Okay, and then we just plug in our values. So if I sub in -10 here, we get negative 10 times 2 is negative 20, minus 1, that's 1 over negative 21. And we can just write that as a fraction. Okay, we don't need to really even do the turn it into a decimal. And the next one, if we put negative 100, we get negative 201 in the denominator. So you have negative 1 over 201. And that pattern continues. If you put in 1,000, you get negative 1 over 2,001. And if you do 10,000, you get negative 1 over 20,001. Regardless of what's happening, you can see that as you move further and further to the left, this fraction is always negative. This number is always negative, but it's getting closer and closer and closer and closer to 0. Will it ever be 0? No, but it gets closer and closer and closer. Same strategy on the next side. We're going to put it in, and we're going to end up with 1 over 19. It's positive. If we put 10 in, we get 2 times 10 is 20, minus 1 is 19, 1 over 19. And just speeding up the process a little bit, the next value is 1 over 199. The next is 1 over 1999. And the next is 1 over 19,999. And again, you can see it's all positive, so it's above 0. It's above the x-axis. And it's getting closer and closer to 0. So it's always coming down, 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 closer and closer to 0, but it will never, ever touch 0. So what do we say to finish off this statement as
fx approaches 0.
Good. And when we do this, we would also write that it's approaching 0 from above. Okay? And on the next one, as x heads to infinity.
So wait, does from above mean that asymptote is above, or that?
It just means as we're looking at the graph from the direction that we're being asked to. So this time we're looking at as x approaches infinity, we're heading this way. So x, the value of the function, y, or f of x, is getting closer and closer to 0. It's approaching 0 from above. It's not approaching 0 from below, which would look like that. Does that make sense?
Yeah.
F of x approaches 0 from... And I think I wrote that wrong.
Yeah, I got
this one is
confused when you
below.
wrote from above.
Sorry. As x approaches negative infinity, f of x approaches 0 from below should be the first one.
Yeah.
And this one from above. And then we have enough information to finish out our graph, which means we can also see our range. Step D, or is it E? So this is D, a little drawing. E, range. Y belongs to a set of real numbers, but what's the restriction on Y?
Y isn't equal to 0.
Y also cannot equal 0. Why will it never equal 0? Well, because you have a 1 in the numerator. So it can possibly be 0. It's always going to be 1 over something. Okay. In example 2, we're asked to determine the x and y intercepts. So we're given the function g of x equals 2x plus 5. Notice it doesn't have to be a 1 in the numerator. Okay. What does this? This is really just 1 over x plus 5 times 2. Okay. Still a linear function. The reciprocal of a linear function, as long as it doesn't have a variable in the top, it will still be considered the reciprocal of a linear function. But you will see how the number on top does change things. Okay. And eventually we'll have a whole list of changes that can happen, or transformations that can happen, or important key information like x-intercepts, y-intercepts, vertical asymptote, horizontal asymptote, and you'll be able to get them just by looking at the equation and knowing a couple of tricks. So anyways, we're hoping to get to that point. How do you solve for the x-intercept?
You set y to 0, or fx to 0.
Thank you. So we have 0 equals 2 over x plus 5. Is there any value of x that will make this true?
X equals -5, which is going to equal 0.
Then it would be undefined. So the same as the situation we were just in. You can never make this expression equal 0 because you always have just a 2 in the numerator. So no value of x makes this true. Therefore, no x int. That shouldn't surprise us. That's what we ran into in the last one. No x-intercept. What about to find the y-intercept? How do we do that?
You set x to 0, so we f and then bracket 0.
Okay, so we're subbing in 0 for x, so we've got g of 0, which is 2 over 0 plus 5. Now, in the last one that we did, we did have an x. We did have a y-intercept in the last one as well, but in y equals 1 over x, you don't have an x-intercept or a y-intercept. So you're noticing already how the value in the numerator and how the value added to the x in the denominator, the constant in the denominator, can affect the y-intercept. So here we go. This is 2 over 5. Therefore, y-int is 2 over 5. So now if we were drawing this thing, we could do what we did in example A in order to get the asymptote, the end behavior, the behavior as it approaches the asymptote, and now we also know how to get the y-intercept. Okay? Good. So you have a little example there using h of x. H of x in your notebook, and h of x is 4 over 3x minus 2. And you're told to do all of the same things that you did in example 1 and in example 2. So what did we do? We state the domain first. Well, the domain is found by looking at the denominator and saying what is x not allowed to equal. We have one factor, a binomial factor involving x.
X is equal to 2.
So x cannot be positive 2. Then we're looking at the end behavior near the asymptote. Well, we better find the asymptote first. Okay, we found the asymptote, I guess. If x can't be 2, then the asymptote is 2. We should make sure x equals 2. Asymptote, x equals 2. It will always be the equation of a vertical line in the form x equals something. Okay, horizontal asymptote will be in the form y equals something. Okay, so we found our asymptote. That's helpful. Let's go as x approaches 2 from the left, as x approaches 2 from the right. See if we can do it without making a table here. From the left means we would start at 1. If we sub in a 1 here, we end up with 4 over negative 3. I'm just going to jot down. Maybe I will make the table. What if we sub in 1.5? We end up with negative 0.5, negative 1.5, 4 over 1.5, same as 8 over 3, and it's negative 8/3. Is that true? Yes. Let's sub in 1.9. 1.9, we'd get negative 0.3 here. So we'd get 4 over 0.3, which would be 40/3, and it's negative. I'd say as we're getting closer and closer to 2 from the left, this thing is getting more and more negative. Does that make sense? I think it's safe to say that h of x is approaching negative infinity. So if we're adding some things to our graph as we're working through it, we've got an asymptote, a vertical asymptote at x equals 2. And we've figured out that as x approaches 2 from the left, we're in negative land, and we're going toward negative infinity. So it's looking like this, at least this part of it. Okay, that's all we found out so far. Let's look at as it approaches 2 from the right. So in this case, we're going to be looking at, let's say, the number 3, then the number 2.5, then the number 2.1. And if we wanted to be more exact, we'd go 2.01 and carry on from there. But let's look at what happens if we put 3 in here. We get 3 minus 2 is 1. That's 4/3. If we put 2.5 in there, we get 0.5 times 3, which is 1.5. You get 4 over 1.5, which is 8/3, positive. And 2.1, you got it. It'll be 40 over 3. So it looks like h of x is heading to positive infinity in that case. So again, as we're heading toward 2 from the right, we're going to head up to positive infinity. Be careful with this step. Like I said, I am cheating a little bit because I'm already drawing my curve at the x-axis. We can do that because we know there is no x-axis. Sorry, there is no x-intercept. But once we get into having a function in the numerator and the denominator, you will start to have an x-intercept. Okay? You will start to have zeros and roots. But for now, we know that it kind of looks like that. Okay, what are we looking at next? As x approaches negative infinity, so as we're heading to the left, and then as x heads to the right, and we can sub in some values here in negative infinity land. Let's try -1, -10, -1,000, or -100, sorry. And what values do we end up with? We end up with, first of all, -1 minus 2 is 3, times 3 is -9. We end up with -4 over 9. If we put a -10 in there, we end up with -12, -36, -4 over 36. If we put 100 in there, we end up with -102, -306, 4 over 306, negative. So again, tells us all the values are negative, and they're getting closer and closer to 0. H of x approaches 0 from below. And then as we approach positive infinity, we can put 1, 10, 100 in there. That gives us enough information. Because we know it's a simple one, it's not going to change direction in there at all. So we've got 1, we end up with -1, 3 times -1. Oh, I'm on the wrong side of the asymptote here. I need to go to the right of the asymptote, obviously. So we're looking at 3, and then doesn't really matter what else you put in. Put in 10, put in 100, as long as we're to the right of our vertical asymptote. So if I put in 3, I end up with 4/3. If I put in 10, I end up with 4 over 24.
How often are we going to make these tables?
Lots and lots. As I put in 100, I end up with 4 over 3 times 98. 3 times 98 is 297. 294. 4 over 294. Oh, that's clearly heading towards 0, but it's all positive, so it's from above. And we can draw it out. And I think the last thing we did is the range. Oh, we could do X and Y intercepts. This is like bonus practice here, though. You really got to appreciate the bonus practice, you know? X-intercept. We know there is not an X-intercept because there's nothing that makes it true if we subbed in 0 for Y. There is no X-intercept. Y-intercept happens if we sub in 0 for X and then simplify. So we'd have 4 over 3 times -2, which is 4 over -6, which is -2/3. So we could add that. That's right here. That Y-intercept is right there. That's -2/3. And the range. Range Y belongs to the set of real numbers, or we should maybe be using h of x. Any restrictions on the range? Yes, if we have an asymptote at 2, well, in this case, the restriction is it can't equal 0. So y cannot equal 0, which will be always for the reciprocal of a linear equation. It will always be y can't be 0. So that will be your horizontal asymptote. That won't change until we start putting a variable in the top. So on a test or on an exam, if it says identify the key features of the graph of this function, and it doesn't even tell you like find the asymptote, find the x-intercept, find the y-intercept, it just says find the key features, this is what you're doing. Finding the domain, finding the finding the vertical asymptote, then finding out the behavior at the asymptote from both directions, and then the end behavior, and then the x-intercept, y-intercept range. That's key information. All right, example 3, we get to describe the intervals where the slope is increasing and the intervals where the slope is decreasing. So it's not just where the function is increasing here and here or decreasing, okay, but where the slope is increasing and where the slope is decreasing. Okay, so we're looking at the rational function h of x equals -1/5x plus 2. We know it's going to have 2 branches. Okay, they're on either side of the vertical asymptote. So the first thing we want to do is find the vertical asymptote. That's going to be pretty standard practice. How do we find the vertical asymptote? The vertical asymptote happens where the denominator is 0. So the vertical asymptote is where the restrictions on the domain are. So in this case, we don't even need to find the restrictions, but it's, in a sense, it's the exact same thing. So we've got -2 on both sides, and then divide by 5, we have x equals -2/5, or -0.4. Now, in order to determine the slope and the changing in the slope, we're going to pick a couple of points to the left of our asymptote and a couple of points to the right of our asymptote. So if I'm just thinking about the number line, if we don't know anything else about the graph of this function, we at least know that we have a vertical asymptote here at x equals -0.4. Give it a dotted line so that it looks like it's an asymptote, not an actual line. It is a line, it's just not a graphed line. And what we want to do is pick a couple of points over here and a couple of points over here. And we'll see how the slope is changing. And this will tell us if it's in quadrant 1 and 3, or if it's in quadrant 2 or 4, 2 and 4. But all we want to do is select a couple of points to the left and analyze the slope there. So to the left. We want to see what is happening around x equals -10, let's say. Okay, so we want to find out the value of the function at x equals -10, and we want to find out the value of the function at x equals -9 because we need 2 points in order to calculate slope. Okay, so if I put in -10, we get -50 plus 2, that's -48. We get -1 over -48, that's 1 over 48. Your calculator can do this a lot quicker, this part. It will round you to 0.21. That's the value of the function at x equals -10. The value of the function at x equals -9, we sub in x equals -9, and we get the value 0.023. From there, we can use our slope formula, which is the change in y over the change in x, and plug in what we know. So we've got 0.023 minus 0.021. Again, we're doing this all step by step the first time through it, but it gets a little easier as you go. The denominator is -9 minus -10, and your calculator will give you 0.002. Now that just gives us the slope at one place to the left of the asymptote. That really doesn't give us any information until we test a point a little bit closer to the asymptote. So down here at -10, we know the slope is positive 0.002. That means it's like barely moving, okay? So let's see what's happening as we get closer to the asymptote. Closer to asymptote. Let's see what's happening when x equals -4. So we'll choose x equals -4 and x equals -3. Find the approximate value of the function at each of those places. In your calculator, you end up with 0.056 and 0.077. So the slope between those 2 points, we would run this rise over run thing again, okay? And we'd end up with a slope of approximately 0.021. You say, well, that's a pretty straight across type slope, but it's significantly steeper than our previous slope, okay? So what information do we get from this? Because 0.021 is greater than 0.002, the slope is positive. Okay, we get that from getting two positive numbers. But we also know that as we're looking, this is why we're going to read our points left to right. So we started down here at -10, and then we went to -4 so that we could read it left to right. The slope is increasing. It's positive and increasing. Okay, I'm going to draw that slope so you can see what it looks like. It's right here. This slope is positive and increasing. That is what positive and increasing looks like. This will come back. Okay, this will come back. And you will ask, how do I know if it's increasing or not? Positive and increasing. Could a slope be positive and decreasing?
Yep.
Okay.
But not for this lecture.
Ah, where's the other leg going to be? The other leg is going to be here. And I'm drawing my curve left to right.
Actually, that would be negative increasing, right?
That is positive. It's always a positive slope. It's getting closer and closer and closer to 0. But it's decreasing. It's getting less and less and less. It's getting closer and closer to a slope of 0.
Yeah,
Okay?
but it's a more positive number.
But it's not, the slope itself is not increasing. The value of the function is increasing, but the slope is not increasing. So down in this leg, it's positive and decreasing. Okay? And in order to determine that, we would do the same thing that we did here, but we would pick 2 points to the right of the asymptote. Okay, so I'm not going to do the whole steps, but to the right of asymptote. And this time we would start with a point just to the right. So maybe since we're at negative 0.4, maybe we'd start with 1 and 2. What's happening at x equals 1, x equals 2. Find out the value of the function there. Find out the value of the function there. Get the slope from those 2 points. Okay? And then you might go further away and you'd try maybe x equals 9 and x equals 10. Always organize. There's going to be a lot of steps and a lot of things that you're doing. Try to organize your thoughts from left to right. Okay? And you'd find out what the function is doing there. You'd find out what the function is doing at x equals 10. You'd find the slope of that. You would learn that the slope at x equals 1 is greater than the slope around x equals 9, but that both numbers are also going to be positive, so you'd find out that the slope is positive and increasing. Okay? What does negative and increasing look like? This slope would be negative, that would be negative and decreasing. This slope is negative and increasing. The value of the slope is always increasing, but it will still always be negative. Okay? This one is negative and decreasing. It starts negative and gets more and more and more and more negative. Okay? This one's easy to understand. This one's easy to understand. These ones often get mixed up. So just beware of that.
So increasing just means the slope.
A couple of important possible confusions to clear up. Here, the value of the function is increasing. It's negative, it's getting closer to 0. But the slope is decreasing. The slope is positive. Here it's super positive, then a little less positive, a little less positive. It's getting almost to the point where the slope is 0. It never gets to 0. It never flattens out completely, and it never comes back down. It's always positive, but it is decreasing. The slope is getting closer and closer to 0. The value of the function is also getting closer and closer to 0, but it is clearly increasing. Okay? So the function itself is coming from negative, getting closer to 0. It must be increasing. But the slope is decreasing. It's a positive value that's getting closer and closer and closer to 0. So be careful with that.